Lecture 4, Module 1, DMAIC Measure Stage, Part 1. Data Collection and Data Types. The topics covered in this module will be data collection methods, and then we'll move on to defining the measurement system itself, and then finally, in the next module, we'll measure the process. Process definition. In Lecture 2, we defined the problem. In that process, we also needed to define the process. This was to identify all the inputs and outputs that existed in the process and which ones were critical to quality, critical to schedule, or critical to cost. As we saw, every process is comprised of steps that have inputs and outputs. All these inputs and outputs can be measured and evaluated as to their effect on the process. Now we need to measure these inputs and outputs, and this lecture will focus on what data we should collect. Again, as we've seen in the previous lectures, all processes have inputs, x's, and all processes have outputs, y's. And a process can be described by the formula y equals the function of x. In order to solve that above equation, we need to measure accurately the critical x's and also the y's. Now, as we saw earlier, there are 6 types of inputs to a process that are called the 6 M's: methods, machines, manpower, materials, measurement, and good old Mother Nature. And all of these different inputs will have an effect, all the variation in those inputs, that is, will have an effect on the variation of the outputs. And we also saw that the Ishikawa diagram can be used to help us map a process. And a process map, a more complicated one, illustrates the individual steps of a process using connected symbols. And the symbols are linked in sequence and show items such as what are the inputs and outputs, decision points and the choices that can be made, what data is generated, and the documentation that is generated. The SIPOC, as we talked about, is a form of a process map that connects all the suppliers and their inputs, processes, and their outputs, and the customers that receive them, so opportunities for improvement can be identified. The SIPOC and fishbone cause and effect diagrams will allow users to study relationships between inputs and outputs. And remember process rule number 1, no process without measurement. Metric definition. The first objective of the measure stage is to establish a baseline of the process as it currently is. What's it doing now? This baseline will be used to compare the measurements of the process after we've performed some kind of improvement. If the measurement of the baseline is not done correctly, it may be impossible to determine what the effects of any improvements have been. So it is very important to understand what a measurement is. A measurement is simply a numerical assignment to an observation that you make about your process. And basically a measurement is data. Data will be used as the basis for making decisions and changes. Consequently, it is highly desirable that the data are accurate, precise, and reliable. And they should also be valid. In practice, it is often just really difficult to know what the true value of the things we wish to measure, what they really are. We are really restricted by the tools we use to measure with, the scales we use in the measurement itself, and even the information the measurement system actually gives us. There are also many errors we can make along the way in collecting data and in our reliance on the measurement systems we use. The first thing we need to consider is what type of data we are interested in collecting. Now, there are 4 measurement scales that are typically used: the nominal, the ordinal, interval, and ratio. Now, I'll point out that these are important to know. Those of you who want to get the green belt and take the green belt exam with ASQ or IASSC, you will need to know these things. And if you don't know them, it will show up, and it will show up later on because these things are related to the analyze phase and improve phase, and you may not pass the exams if you do not thoroughly understand these data types. Now, each of these scales has an appropriate use and different procedure for analysis. The nominal scales. These are not actually measurements and are simply labels that are applied to categorical information after you collect it. And nominal is from the Latin nominalis, meaning of names. And here's an example of some nominal values for categories of unit doses. So we might nominally assign vials to the number 1, ampules number 2, tablets 3, capsules 4, tubes 5, etc., etc. Assigning nominal values to categories allows certain statistics to be applied to these data, such as the binomial or Poisson models. Nominal scales, by the way, have no unit of measure. Ordinal scales. These are scales that have a prescribed order to them. The most obvious would be like best, better, good, worst, worst. These scales can be analyzed using mathematical operators, so equals to, not equal to, less than, greater than. And there are a wide variety of statistical techniques that can be applied to ordinal data. And ordinal data can also be converted into nominal data and analyzed using the binomial or Poisson models, if that seems to be convenient or useful. Also, ordinal scales have no unit of measurement. Interval scales. All quantitative attributes are measurable on interval scales. These scales are use defined intervals that are uniform throughout the scale. For example, temperature scales are interval scales. There are several temperature scales out there, Fahrenheit, centigrade, Kelvin, each with a unique interval that sets the range of the scale. But the intervals are fixed in value. So 50 degrees minus 49 equals 1 degree. And 100 degrees C minus 99 degrees equals 1 degree C. It doesn't change. The interval is always the same. That's why it's called an interval scale. These scales are not equivalent. That is, 1 degree C is not equal to 1 degree F. But their values can be converted into each other's scale, as we all know. So conversion from one to another follows the form y equals ax plus b, and with a greater than 0. Many statistical techniques are available for data from interval scales, and interval scales do have units of measure. Ratio scales. These scales are called ratio because a measurement using two different scales are related to each other in a specific ratio. For example, mass can be measured in pounds or in kilograms. The ratio of pounds to kilograms is 2.2. Conversion from one ratio scale to another follows this form, y equals ax. Most measurements in science and engineering are done in ratio scales. Many statistical techniques are available to the data from ratio scales. And ratio scales, again, also have units of measurement. It's important to know what type of scale your data was derived from, so errors are not made by choosing an invalid statistical analysis. However, most data collected in Six Sigma can be classified more simply using two certain types of classifications of data: the discrete data and the continuous data. Discrete data are called discrete when they come from a finite or countable set of discrete values, such as integers. For example, the number of cracked vials out of a total, or the number of vials with visible particles out of a total in a filled lot of biological products is a discrete value. There's only so many of them. Data from nominal scales and ordinal scales are considered discrete. There are specific statistical techniques used for discrete data. Continuous data are the data that exist on an interval or several intervals ratios. For example, the measurement of pH in a bioreactor is on one continuous interval scale that ranges from 0 to 14, as most of us know, but has an infinite number of points, continuous, in between 0 and 14. Also, the measurement of weight on a laboratory scale can be more than one continuous interval scale that have an infinite number of points, continuous. So kilograms or pounds. Data from interval scales and ratio scales are considered continuous. There are specific statistical techniques used for continuous data. And the relationship between those scales and the classifications of the data, the nominal and ordinal are discrete, and the interval and ratio are continuous. Now, once we know what type of data we're going to collect, we can then address data collection. There are three ways of collecting data: a census, by sampling, and by experimentation. Census. When data is collected from the entire population that you're interested in, this is called a census. When hearing the word census, the most people think about the census that's taken every 10 years on the entire population of the United States, thereabouts. Taking a census is very expensive and time-consuming, usually impractical, and sometimes it seems impossible. However, the census is actually used quite frequently in the pharmaceutical industry. It's quite often seen that finished products are subjected to what's called a 100% inspection. If a foreign tablet is found on the line, and it's possible that another foreign tablet may have entered a lot of other tablets, the quality assurance department may dictate that all of the finished product that has been manufactured on that line needs to be inspected. So 100% inspection. And this is a very conservative approach. Again, looking for that one rogue tablet. And then it may even get worse than that they may ask for 200% inspection where they do it twice. Just trying to reduce their risks. And these types of inspections are just examples of a census. Sampling when data is collected from only a portion of the population that you're interested in. It is important that the sample collected from the population is representative of the whole population. In 1936, a magazine conducted a survey of the voting population asking whether Franklin D. Roosevelt, a Democrat, or Alfred Landon, a Republican, would win. The survey predicted that Landon would easily win the election. However, Roosevelt won by a landslide. So how did that happen? Well, for one thing, the survey was conducted using the telephone. In 1936, most people with telephones were quite wealthy, and most people didn't have them. And this class tends to always vote Republican. So they sampled from the wrong population. The survey sample was not representative of the actual true voting population. Now, there are several techniques for collecting representative samples. Simple random sampling, systematic random sampling, cluster sampling, stratified sampling, and sequential sampling. Simple random sampling is a procedure for which every possible sample of a population is equally likely to be chosen. There are two types of simple random sampling with replacement, and simple random sampling without replacement. Simple random sampling with replacement is when the sample is returned to the population after sampling and may be selected again. Now, this is done for populations that may be sampled again and again. The removal of members of the population changes the probability distribution of the population. Every time you take some samples out, you've changed the characteristics of that population. For example, a sample of 100 from a population finds 3 defective samples. If these 100 samples were not returned to the original population, the next sample will have a much lower probability of finding the defects. Simple random sampling without replacement is when the sample is not returned to the population after sampling and cannot be selected again, which of course changes the population. However, this is more common than random sampling with replacement, especially with destructive tests where you maybe tested a tablet for assay and it's gone now, so there's no way to return it to the population. Simple random sampling is normally performed using a random number generator. Random numbers can be obtained from a random number table, or Microsoft Excel can be used to generate random numbers, or more likely, statistical software packages such as Minitab can generate random numbers, and this is more likely to be used these days. Systematic random sampling is a procedure where the samples are chosen using an interval, k, also called the skip interval, how many you should skip, of the population based on the sample size chosen, small n, and the population size, big N. The formula is simply this: k equals big N divided by little n. So, for example, if we wish to take a sample of 500 blister packs for inspection from a production run of 118,282 blister packs, 118,282 blister packs, we would take a sample every 236 blister packs. So 500 divided into 118,282 gives you 236. Now, it may be more convenient to round that up to 250 or something like that, which makes it convenient to sample so many blister packages or something like that. But it gives you an idea how to get a systematic random sample. Cluster sampling is used when members of the population of interest are not in the same location, and traveling from location to location is inefficient and costly. For example, a pharmaceutical company may want to hear the voice of the customer on a global system, such as an order replacement system that they're using, and interview the users. Now, visiting all locations around the world is much too costly and time-consuming. So you might consider creating a cluster, such as the North American, the Central American, Eastern Europe, Southeast Asia, Australia, New Zealand, etc., and sampling some of the locations in each cluster is a much more efficient and much less costly sampling strategy. However, the locations in each cluster would need to be sampled by what's called proportional allocation, meaning the number of locations sampled in each cluster would be proportional to the total number of locations in the cluster. So one cluster in maybe Australia and New Zealand only has 10 locations, but in North America there's 500 or something like that. So obviously you're going to sample fewer in the Australia and New Zealand and much more in North America. Stratified sampling is a process of dividing members of a population into homogeneous subgroups before sampling. When there are subpopulations within the total population of interest, then it's better to sample each subpopulation independently. For example, a pharmaceutical company has received complaints about poor seals on several of its product packages. They have many products and want to sample the products in their warehouse to see how pervasive this problem is. They classify the products into strata and then sample the strata using random sampling with proportional allocation. Makes it easier. Sequential sampling is used when testing is destructive and the tested units are expensive, so minimal testing is really desired. In sequential sampling, a fixed sample size is not used. Instead, samples are taken and analyzed one after another, and the sampling is stopped as soon as specific results are achieved. For example, if 3 samples in a row pass, accept a lot. If 2 samples out of 3 in a row fail, then reject a lot. If 1 sample out of 3 fails, test 2 more samples. If both pass, then accept a lot. If 1 more fails, reject. This approach can substantially lower the cost of product lost through sampling and of the time spent in the analysis. Experimentation. Data is also collected through experimentation. However, this will be discussed in more detail under design of experiments in the analyze phase. Data collection methods. There are various techniques used to collect or record data, and there are 2 common types: check sheets and data sheets. Check sheets, these are forms with a list of items or events with a place to record if the item or event occurred and how many times. Coded data. You can create check sheets that may record data using a number, letter, or a symbol to identify an item or event for ease of analysis later on. For example, you may decide to say tablet defects could be coded as chip tablet equals 1, orange peel on a coating equals 2, etc., etc. To facilitate recording, instead of writing chip tablet down 20,000 times, and statistical analysis later on. And here's an example of a check sheet. So the product is capsicum 100 milligrams, being run on tablet press Fetty 3090, number 3, and there's a date in the analyst. And here we're looking at the first shift, so we're looking for the defects: chipped, picked, sticking, capping, lamination, hair, and black spots. So at 8 a.m. we had 1 chipped tablet, and we had 6 picked tablets and 3 sticking. And at 9 a.m. and 10 a.m. and 11 a.m. we see a continuation of the picking going out to 3 o'clock and then tapering off. Sticking disappeared after 11 o'clock. And we see randomly occurring issues with capping and lamination. We even see 1 hair at 3 p.m. And believe it or not, hair is a defect in a tablet, and that's why people wear beard covers and hair covers, and they still get into the tablet sometime. Now notice on the total you have the rudiments of the beginning of a Pareto chart, which we'll discuss later on. So we have values for each one of these types of defects, and obviously it stands out that picking has 31 instances, so it's obviously one of the bigger problems that we have on these tablets. The hair and lamination are the lowest, and black spots we had 2, but that they both happened at the same time. It may be just a one-off instance. Again, we have to analyze that data later on. Data sheets. These are forms with a place to record specific results of an analysis during a study. It is common and a very good practice to include data sheets in validation protocols to avoid missing taking samples or recording data, and this practice is also wise for Six Sigma projects as well. It's become popular to use Excel to collect data. However, care must be taken in designing the worksheets for collection of data with the subsequent analysis requirements in mind. You can create very pretty spreadsheets, and they look really, really nice, but there's no way that you can analyze the data that you've collected in them. So you need to be very careful about the way you're going to collect the data. If not designed well, it can be impossible to analyze the data in Excel later on, requiring reworking the data, losing time, and guaranteed you'll introduce errors. Mistakes will be made in transposing numbers or typing them in wrong. And an important note, Minitab requires data to be in columns. So if data will be imported into Minitab from Excel, it must be set up in a design that can be analyzed in Minitab. Otherwise, it will be impossible to analyze the data, and you will spend hours and hours and hours fixing all the data and probably making more mistakes. And finally, let's talk about some errors that can be introduced into data collection. Be aware of. The Hawthorne effects theoretically occurs when individuals, workers in particular, are being experimentally observed or measured, actually improve their performance in response to being studied, and not in response to the experimental factors being studied. The Hawthorne effect originated from some experimental results at the Western Electric Hawthorne Works factory. Hawthorne Works had commissioned a study to see if its workers would become more productive in higher levels of light. Give them more light, they'll see better, they may improve their productivity. The workers' productivity definitely improved when the light levels were increased, but then they dropped again when the study ended. And this was examined and looked at 10 different ways. And finally, someone said, let's do another study. And let's look at the effect of lowering the levels of light. And guess what? Again, the productivity improved. Why? Well, the productivity gains were attributed to the motivating effect on the workers actually being watched as they're working. Think about your parents saying, Grandma's coming over, so remember to be on your best behavior. Or if you've ever had somebody visit that's important to you, obviously your behavior is much better than if there's nobody around. So keep in mind that the Hawthorne effect may be present in individuals that know that they're being evaluated. And this is an example of bias.